Linear programming and optimization. Optimization is one of those great areas of mathematics where you can really see the application of the math that we are learning. So in optimization, there are quite a few different parts, but everything that we've done in this lesson or in this section has kind of led up to this. So what we have in an optimization question is we're trying to minimize or maximize something called an objective function. So in this example, our objective function is z is equal to 10 times x plus 3 times y. So we're trying to find the min or the max value based on the endpoints of our feasible region. So we're going to have this objective function. You're going to have a system of inequalities, which is what we just learned about, a system of inequalities. We're going to graph that feasible region, which is the part that is shaded. And then we're going to find the vertices of the feasible region. So 2, 0, 2, 3, 5, 3. So I used this example because we worked on it in lesson 7.5, which you may have just finished watching. So I have 3 endpoints, and then what I'm going to do with those endpoints is I'm going to take that objective function and I'm going to plug in each of those endpoints, 2, 0, 2, 3, and 5, 3. And then depending on the context of the question, whether I'm trying to minimize or maximize, I would say the minimization would be at the point 2, 0, because 20 was the lowest value. 59 is the greatest value, so if I'm trying to maximize, I'm using the point 5, 3. So that's a good overall view of what we're trying to do, but let's go ahead and now kind of get into it and work through one together. Let's take a look at how to minimize an objective function. So this is one we're kind of starting from scratch, and I want you to notice I'm going to use Desmos exclusively, and you are welcome to do so as well for this section. So if you'll notice, I already have all of the constraints. So there are the fact that x and y are both greater than or equal to 0, just meaning we're dealing in the first quadrant only. And then we have the other 3, not objective functions, excuse me, the other 3 constraints. And it gives us an idea of what that region looks like. So again, I'm going to show you how to best do this so that it minimizes your work. So as your instructor, my goal is to make sure that you understand it. So I'm not going to make you go through the unnecessary steps of graphing all of this by hand and shading it by hand and plugging things in by hand. We're going to utilize Desmos for all of that. So what I'm going to do is I have all 5 of my functions. I'm going to add a table, and in that table I'm going to make it so that it connects with a line, and I'm going to just start plugging in points that define the corner points of my shaded region. So it kind of looks like a mess right now because I have so much stuff shaded, and if you want to get rid of some of the shading, we know that we're looking for a region that is in the first quadrant. That's the x is greater than or equal to 0, y is greater than or equal to 0. And it looks like this shaded region right here. Now, by getting rid of these 2 functions, I'm no longer able to click on that point of intersection, so I would suggest to you to click on the point of intersection first, to plug in that point, and then kind of go clockwise or counterclockwise, whatever you want, to start plugging in the next point, 0, 40, 30, 45, the next point would be 60, 20, and then 50, 0. And then I'm going to go back to 0, 0. So what I suggest is plugging in all of those points and then just getting rid of all of the other shading. So we have to shade it till we can see what the endpoints are, but then once we know the endpoints, it doesn't matter to me if it's shaded in the middle. And from here, remember what we're trying to do is we care very much about the endpoints, but not only the endpoints, we care about what is the value of the objective function at each of those points. So in order to find the value of the objective function, I could say 12 plus 0, or 12 times 0 plus 8 times 0, and find each one in a separate line. But you all know that I'm far too lazy for that. So instead, I'm going to say z1 is equal to 12x1 plus 8y1. And notice the magic that happens. It says 6-element list. Now, you would think you could be able to just click on that and find out, but you can't, but that's okay, because what I'm going to do is up on my table, I'm going to tab over and just enter Z1, and voila, this is the value of the objective function at each of those points. So if I'm looking for a minimum, the minimum would be at 0, 0, because 0 is the least value. If, for instance, I was looking for a maximum, then I would be at the point 60, 20. That would be the maximum value of 880. But the minimum, because that's what we're asked to do here, is at 0, 0. Let's do a practice question. I'd like you to try this one on your own. We are maximizing the objective function z is equal to 12x plus 8y. And I've given you the constraints that x and y are both greater than or equal to 0, and an additional 4 inequalities. I'd like you to press pause, try this question on your own. When you're ready, press play to see how you did. So as a reminder, my first step was to enter all of the constraints in inequality form to determine which area is shaded for all, in this case, 6 inequalities. And to me, it appears to be this shape right here. So I'm just going to click on the points that outline the outside of it. And I have, 6 points. And I'm going to use those points to create all of the 6. Now notice I have 7 because I'm following it around the region, and then I end up back where I started in order to just make a closed shape. That helps me to visualize the region a lot easier than having all of the shadings on here. So here's what I'm looking for. Now, if you're very interested in making sure the shadings are on there, remember all that you have to do is take one of the inequalities, and simply start adding the other inequalities as constraints. And you can do that for all of the other inequalities. So I'm going to take all of these, and ideally, when I'm done, only that region in the middle will be shaded. And so continuing, almost there. I have one more constraint, and hopefully when I click on that, it's going to look shaded just in that one region. And there we go. So again, if you want it shaded, you just have to choose one of the inequalities and add all of the other constraints as restrictions in that one equation. Now, I'm going to go ahead and get rid of all of these just to make it easier to see everything on the screen at one time. I have included the objective function, z is equal to 12x plus 8y. Remember what I did last time is I changed this to z1, and then I'm telling Desmos to use my values for x1 and my values for y1. And that's going to give me a 7-element list. So I'm going to choose z1, and it's going to find that value for me. Now in this case, I'm looking for a maximum value, so I can just inspect and find that 96 seems to be the maximum at 6.3. You can also use max z1, as you can see here, and it gives you the output of 96. It's really up to you. You don't need to use the max function if you don't want to, but it's just an easy way to find that solution. We're going to end with 2 application questions, and I've split each of them into 2 slides so that for the first slide we can take a look at writing the constraints and the objective function. And for the second slide we can look at Desmos and graphing, finding those corner points, test points, plugging them into the objective function, and finding the minimum or the maximum. So to begin here, if you need to, pause for a moment and read through the question. So I'll assume that you have read the question already. We have a carpenter that makes bookcases in 2 sizes, large and small. So all of the things that we are asked to do here will relate to large and small bookcases. We need to tell the reader, what does X represent and what does Y represent? So I'm going to let X represent the number of large bookcases, and I'm going to let Y represent the number of small bookcases. That allows me to use X and Y throughout this question without wondering if the reader knows what I'm talking about. Now I'm going to start reading through. It takes 4 hours to make a large bookcase, so 4 hours for large, so that's related to X, and 2 hours to make a small one, so that's 2 related to Y. And the profit, so now we're talking about profit. The profit on a large bookcase is $35, so that's related to X. And on a small bookcase is $20, so that's related to Y. The carpenter can spend only 32 hours, I'm going to switch back to yellow because that was hours, 32 hours per week making bookcases, and must make, and this is not related to anything else, must make at least 2 large and at least 4 small. So at least 2 large would be related to X and at least 4 small related to Y. How many of each should the carpenter make to maximize the profit, and what is the profit? So we have 3 different relationships happening. We have the one that I've boxed in yellow, the one in green, and the 2 in red. So let's take a look at how I can relate those into constraints or an objective function. In terms of the objective function, we know that the objective function will have everything to do with the question, and the question is talking about profit. So in this case we have 2 questions, maximizing the profit and what is it? So how many of each? So the objective function Z is going to be related to profit, and the profit is what I boxed with green. So Z is not going to be related to an outcome of say 100 or 200. We're saying Z, which is the profit, can be found by taking 35X plus 20Y. Again, where did I find that? Because I make a profit of $35 on a large bookcase and $20 on a small bookcase. So that's my objective function, and I'm going to go ahead and cross those out because now I've used those values. Let's take a look at the yellow, what I've boxed in yellow. We have that it takes 4 hours to make a large bookcase, and it takes 2 hours to make a small one, and I have to spend 32 hours or less. So can only spend 32 hours means it can't go over 32 hours. That's a constraint. Let me cross those off. Now I've used them. So now I have the 2 that I've underlined in red. The carpenter must make at least 2 large and at least 4 small. There's no other thing to relate to that, so those are going to be 2 separate constraints. So the number of large has to be greater than or equal to 2, and the number of small has to be greater than or equal to 4. So these are my constraints. Here's my objective function, and don't forget to say what X and Y represent. So now I'm in Desmos, and I have graphed the 3 functions for my constraints, and I can see that it gives me a triangle figure with 2, 12, 2, 4, and 6, 4. So I'm going to create a table with those endpoints, and that was 2, 4, 2, 12, and 6, 4, and then I'm going to go back to 2, 4. And I'm going to go ahead and add the line so that I can kind of get rid of the riffraff. So this is the figure that I'm worried about. And again, if you really want it to be shaded, you can click on the shading and then add the constraints that x is greater than or equal to 2 and that y is greater than or equal to 4, and that does the shading for you. So from here, now I have to use the objective function, which is that z is equal to 35x plus 20y, and I'm trying to maximize profit. So I'm just going to change that to z1, x1, y1, and that gives me 4 solutions. So I'm going to arrow over and add z1, and it's going to give me those values. Now, obviously, the first and last values will always be the same because I'm adding them twice in order to make a closed figure. But what I'm looking at is to maximize the profit, how many hours, how many small and large bookcases, and what is the profit. So the largest profit is 310, and that occurs when x1 is 2 and y1 is 12, which means the answer to my question is the carpenter should make 2 large and 12 small bookcases to make a maximum profit per week of $310. We're going to finish up with one more application question. If you would, press pause, use this time to write the objective functions, write the constraints, assign your variables, and then go ahead and pop over to Desmos and find the solution as well. When you're ready, press play to see how you did. So in this question, we're dealing with flying bats and flying falcons. So I'm going to let x be the number of flying bats, and I'm going to let y be the number of flying falcons. It says that because of supply materials, no more than 40 flying bats can be built each day. So x, the number of flying bats, has to be less than or equal to 40. It says, and that's from no more than 40. No more than 60 flying falcons can be built, so y has to be less than or equal to 60. There are enough workers to build at least 70 toy airplanes each day, so that's total. I'm going to go ahead and switch colors on that. At least 70 per day, which means the number of bats and the number of falcons together can be greater than or equal to 70, so 70 minimum. It costs $12 to manufacture a flying bat and $8 to build a flying falcon. What's the minimum possible cost each day? So minimum is dealing with cost, and that means that's the objective function. Z, it costs $12 for a bat, so 12x, and $8 for a falcon, so 8y. I add that together to get the total possible cost each day, and I'm trying to minimize that. So let's pop over to Desmos and plug these in to solve. In Desmos, as you can see, I have graphed the function. It is shaded. I do have the endpoints 1060, 4060, 4030, and then back to 1060. And that gives me the outline of my figure. Whether or not you actually shade it, as long as that region is enclosed, so I can see that you have found all of those endpoints. My objective function was 12x plus 8y, and I'm trying to minimize. So you can use the minimization formula, or you can simply look at the list and see that the minimum possible cost is 600. It didn't ask, but that would be for 10 flying bats and 60 flying falcons. Coming up next is Chapter 8, Matrices and Determinants.